Okay, so we can start today's lecture. So, hello everyone, good evening. So, today is the week two of the course of physics of nanomaterials. And last week, we talked about the nanotechnology and nanomaterials. So, we saw that why nanotechnology is significant in nanomaterials. So, what was this? So, so nanotechnology, what was it involving? So it involves the manipulation of matter on an atomic scale, molecular and supramolecular scales. So the size was of nanometer was up to 1 to 100 nanometers. And why is it so? Why nanotechnology is so significant in nanomaterials? That lies in the ability to engineer materials we, with which we can have the novel optical, electrical, magnetic, and mechanical properties. So, we saw in the previous lecture that when we are moving from bulk to nano materials, the properties were drastically changing from their bulk counterparts. So, that enabling us for advanced application in medicine, electronics, and energy storage. And we also saw that higher surface to volume ratio when we are dealing with the nanomaterials, and the quantum effects were dominating that will lead to the unique physical and chemical characteristics which were making nanomaterials highly desirable for catalysis, delivery, composite materials, and nanoelectronics. So this was all which we which we went through in the last week. This week we will talk about the quantum confinement, energy bands, and the crystal behavior at the nanoscale. So we saw we have already uh, So we saw that when particle in a box or to real nanomaterials, how the confinement, periodicity, and size together will decide whether a material will be material will be conducting, insulating, or dielectric. So this in this lecture we will cover the quantum confinement. Like in that case, we will see why the nanoscale electrons stops behaving classically, and we have already read in the quantum mechanics we deal with the particle in a box, and that according to that model we can explain that. Next is energy bands, how the bands form in case of solids, bulk materials. Then what is the change in the crystal structures and phase transition when we were moving from the bulk to the nanoscale. And last, uh, how the band gaps resistivity and electrical behavior changes when we are moving from the bulk to nano dimensions like 1D, 2D, and 3D. So, first part we will deal with the quantum confinement and the particle in a box. So, we will in that case we will see that how free electron models breaks down at the nanoscale and how confining an electron in a tiny region quantizes its energy. So, to understand this, first of all, we are moving from the bulk to nano size. So, to explain the behavioral changes, there were two models. One is Drude model and the other one is Sommerfeld model. So, there are two classical pictures came uh, which could explain the electrons in bulk matters. But what was the common point in that? Like in both the models, it was assumed that the metal is effectively infinite in size. But in actual, we know that obviously a material is not infinite, it is a finite size and shape. So, in case of this was the common in both the models. Now, what were the changes in Drude and Sommerfeld model? In Drude model, we considered that the positive ion, that is nucleus, is fixed and the electrons are moving freely inside the chamber. So it is behaving as a classical gas of charged particles. What could that model could explain? It could explain the Ohm's law, thermal conductivity. I will. So there are few questions on this. So at that point, I will explain the formula also, like how is it deriving. So what does this root model could explain us? Ohm's law, thermal conductivity, but it could not explain the electronic heat capacity or quantum mechanics. Why is this so? Because there were two main reasons. First is they considered a constant potential, and there was and electrons are fermions. So we have to consider the Fermi-Dirac statistics, which was not considered in the Rood model. Next, Sommerfeld model came and it added the Fermi-Dirac statistics and Pauli's exclusion. So it could predict the heat capacity and Fermi energies, but still it also assumed a constant potential, no lattice, no boundaries. So it couldn't give the whether which metal will be metal, semiconductor, or insulator. So that's why, like, we need some other metals. So then comes what is, so to understand, like when we are saying the quantum confinement or electron confinement, what does this mean? So quantum confinement occurs when the physical dimensions of a material are reduced to the same order of magnitude as the de Broglie wavelength. So in that case, if we are restricting electrons motion in a region smaller compared to the de Broglie wavelength, we can't treat the electron as a free particle. So it means now the allowed energy will become discrete just like an atom. So we defined in the last class that what are nanomaterials, in which we have at least one dimensions between 1 to 100 nanometers. And the when it is when the confinement becomes important, what is the trigger point? So when the particle size will be compared to the electron de Broglie wavelength, then the confinement becomes important. And what is the consequences of the confinement of the electrons? It will give us the transformation of the continuous energy bands into discrete quantized energy levels, which will affect the material's optoelectronic properties. So now the we have to explain the properties of the uh, materials by the quantum mechanics, not by the classical physics. So what we saw that we have Drude model. So that was a classical model which were describing electron transport in metals, where we were treating electrons as a gas of free particles, and where the positive ions were stationary. So it couldn't explain the any quantum phenomena, but it could explain the basic electrical and thermal properties like Ohm's law. Then Sommerfeld model came, which improved upon the Drude model by applying the Fermi-Dirac statistics to the electron gas, and it could explain us the electronic heat capacity. So, next was there were we saw that there were three types of confinement, that 1D, so 0D, 1D, 2D. We saw that. So if we are considering, if there is 1D confinement, it means quantum well, that is free motion in two directions. And if we are considering quantum well, that is 2D confinement. So here the free motion in one direction, for example nanowires. Then quantum dot, where there is no free motion. The examples are quantum dot. So first of all, we are considering that particle in a box. So you can consider 1D box, 2D box, or 3D box. Depending upon that, we can describe the potential in the three direction. So here we are considering in only in one direction. So if I am considering particle in a box, that is I am confining my electron. So electron confinement, we can do it in one direction, two direction, three direction. Here we are considering only x in, for a single direction. That's why we are defining the potential uh, for in the x-axis only. So v potential is zero, and in potential is zero within the boundaries of the box, that is lies between the region 0 to a, and outside that boundary the potential is infinity. So we know that the time independent Schrodinger equation minus, so since the walls are infinitely high, the wave function must be exactly zero, and outside the box this is continuous, and the from 0 to a the potential will vanish. So here we are defining a quantum well. So how to solve this equation? If we solve that Schrodinger wave equation, the general solution for this is given by psi x is equals to a sin kx plus b cos kx. So now we will apply the boundary condition. So how can we define the like what is wave function? So wave function, we can define the wave function as a mathematical description of the quantum state of a particle or a system. So in nanomaterials, psi x square will give us the probability density of an electron's location. And here when I am saying the boundary condition, what does this mean? So these are some mathematical constraints when we are applying to the wave function at the physical boundaries of the system. So for this box, what are the physical boundaries of my system? That is uh, psi is equals to 0, like x is equals to 0 and x is equals to a. So you can see in the second, at the second point, we are considering at x is equals to 0, which is one boundary, and where we saw that the potential was infinity. Potential was 0. So psi 0 is equals to 0. So you can, if you will substitute that x is equals to 0 value in the first equation, you will find out that a sine 0 is equals to that, it will become 0. So this part will become 0, and here b cos kx cos 0 in 1, so b is equals to 0. So obviously it is not possible. So then at x is equals to a, so sine ka is equals to 0. Now we can define the ka is equals to n pi. So from here we got the allowed wave vector k is equals to n pi by a. You can see that a is the size of the well. So here, which is a well, x is equals to 0, x is equals to a. So now depending upon this size, our wave vector will change. So what it give, so what does this what is it representing? That, so the wave number is quantized, which is given by n, k is equals to n pi by a, which forces the energy itself to take only the discrete values. So yeah, so if we will find out the formula, n square, so en is equals to n square s square, where a is the dimension of the box. So we saw that this energy is depending upon en is proportional to n square by a square. All are the other, h is Planck's constant, pi is constant, mass is constant, 2m, all are constant. Only The energy is depending upon the value of n and a. So we can see that if the n is increasing, then En is increasing proportional to the n square. Means the energy levels will be far away as the n increases. So this was the first point. Energy is grows as n square. So the energy levels will spread further apart as n increases. So you can see that if I will substitute n is equals to 1, it is given s square pi square 2m square. Suppose it is even. Next, when we will substitute E2, it is equivalent to 4 even. Then it is 9 even. So as the n will increase, it will become far apart. And when a is and En is energy scales as 1 by a square, it means if the box dimension will decrease, the energy will increase. So that's why we saw that if the nanoparticle size was decreasing, the band gap will change and the band gap will increase. And if the band gap will increase or change, then depending upon the size of the nanoparticle, we will have the uh, different colors of the nanoparticles. So you can see that we have represented for n equals to 1, n equals to 2. For 3, 3 square is 9, 9 even. And similarly, we'll go. Next is how can we define the wave? So we understand about the energy quantization that we we are restricting a system's energy to specific discrete values. And what were these discrete values? That E1, 4 E1, 9 E1, 16 E1. So in nanomaterials, this from where it is arising when we are considering the time independent Schrodinger wave equation, and that is responsible for the, so when the quantum confinement will happen, it will be responsible for the size dependent behavior, such as we show in the shifting emission colors of the quantum dots. So as explained the wave function, that it is a mathematical description of the quantum state of a particle or a system. Then what is probability density? So it is defined by the psi nx square. So you can see that. uh, so for psi 1, you will write the wave function. So for n is equals to 2, it will give us the odd function. And similarly, we can plot the probability density also. So the next important concept comes is density of states. So density of states tells us how many quantum states are available, and it represents the number of allowed electron states per unit energy interval. So that is the E is defined by number of allowed electron states per unit energy interval. So if we are considering, so it also depends on the which in 1D or 2D or 3D. So for the one dimension, the density of states diverges at low energy, and when the energy is rises, you can see in this plot, since the dependence for 1D is E proportional to minus half, and for so this E minus 1 by 2, you can see that so in case of nanowires, that is 1D, it is stating at one dimensional confinement. So density of states varies as E power minus half. So that this is what I was talking about, that if we are changing the quantum dot size, the emission colors are different. So here you can see that the only the size is changing, chemistry is same. So depending upon the size, the band gap will change and the emission will shift. So now, so when we how the bonds are formed, why in the solids the bonds are forming. So now we will talk about the band theory, which will describe the quantum states that electrons can take in a solid crystal and creating energy bands which will be separated by some band gap. So how is it happening? So in a single isolated atom, if we are considering a single atom, we will have a discrete energy levels. Since we just now we saw that we will have a discrete discrete energy levels. Now if we will increase the number of atoms, n is equals to 2, n is equals to 3, the number of energy levels will increase within that distance. So now we have in the bulk level, at a macroscopic crystal we have n is equals to 10 raised to power 23. So and when these atoms, the interatomic distance will start decreasing, then these levels will form a continuous energy band because the distance is not very large but the energy levels are very energy, because energy levels will increase within that smaller gap. So and when it will come a particular equilibrium interatomic spacing, the bands from different atomic levels may or may not overlap. That's why it is giving us a forbidden gap, band gap between valence and conduction band, which is we call a band gap. To understand this, like the form for the formation of bands, there was one theorem came into picture which describes the periodic potential, which is the Bloch theorem. So Bloch theorem states that, so in the crystal we have the atoms like this. It has periodicity A, and here each and every atom will face some potential, and the potential is periodic. So what does this theorem states that? It states that the energy eigenstates of an electron in a periodic crystal can be described as plane waves. So this is the plane waves, and which is modulated by the periodic function. So here this is given by the periodic function. So what is the theorem? It states that the energy eigenstates of an electron in a periodic potential uh, can be described as a plane waves which is modulated by, since it is arranged linearly in 1D only, periodic function. So that is, so this Bloch theorem, so in a real crystal that potential is Vx, so that the electron will feel, so if the electron is coming and it is traveling inside the crystal, it will feel repeats with the lattice period. So at each A, it will feel that potential. So it will have the form of psi x is equals to exponential iota kx. Sorry, exponential iota kx dot ukx. So where uk is the period, it will follow the periodicity with the lattice. So that will define the plane wave part. This is defining a periodic part which modulate that the wave with the same period as that the atomic lattice. Next is to define the, so we are defining the bands using the KP model, that is Cronin Panay model, in which we are considering a periodic square well potential. So it replaced the, like we are having a repeating series of square barriers which have the periodicity A plus B. So we will solve after solving the Schrodinger equation separately inside the wells and the barriers. Then after we'll apply the Bloch's theorem and the boundary condition. Then according to Cronin Panay model, we can explain which is where we are getting the allowed energy bands, and which material is a semiconductor, metal, and insulator. So this is the ek diagram, wave vector and energy E. This k is equals to minus pi by a and pi by a. This is the brilliant John boundary. So here we are so we know that the allowed states, so we have valence band, we have conduction band. In between this, there is no energy level, and this is the band gap. This is the forbidden gap. So higher bandwidth, so we can, you by using this, if there is no band gap between the valence band and conduction band, that is no bands, no gap, bands are overlapping. So if there is a overlapping of the bands, it is considered as a conductor. If the energy gap between the valence band and the conduction band is smaller, is approximately of 0.1 to 3 electron volt, then it is considered as a semiconductor. If we have the band gap larger than the 3 electron volt, uh, then we we say it as insulator. So on the basis of KP model and by using the Bloch theorem, by considering the periodicity of the lattice, we are able to explain that we what uh, we were able to differentiate between the metal, semiconductors, and insulator, which we were not able to define using the uh, which were not able to explain using the Toad model or Sommerfeld model, because in that case we were considering that the potential is constant. So here that is not the case. Next is, so next what is, so if we are talking about the crystal, then how the crystal, what is crystal lattice? So first of all, a crystal is made up of lattice plus basis. So, how do we define the lattice? Lattice is an abstract, infinite set of points repeated periodically. So here we are we are defining the, there is no atom, just a geometry, like it will lie here, but no atoms assigned it. Now, when we are considering uh, atoms, if we are giving the atoms to each lattice point, then it is called basis. So it can be of one atom, or it can be small group of atom, one, two, which is attached to every lattice point. So by combining the lattice plus basis, we are having the real physical crystal. That so so in the crystal also there are. So now we have defined the crystal lattice. So what is crystal lattice? It is the, so we can define it as the ordered periodic 3D arrangement of atoms or molecules. Since if it is a group, then we are saying it molecules in a solid. Now, depending upon how the properties of the nanomaterial will change, its geometry. How the geometry will change? So by changing the geometry will significantly impact our nanomaterials properties. So when we will move from the bulk to the nanoscale, high percentage of the lattice atoms will be located at the surface. So if I'm considering this as, so this is upper surface, this is the bulk part. So nanos at the nanoscale, what will happen? The lattice atoms will be located at the surface, and which will in like introduce the strain surface states, which we'll see in the question part later, that how the uh, what is happening with the lattice constant when we are increasing when or decreasing the lattice size. So there are two other terms. One is unit cell and the other one is primitive cell. So what is unit cell? The unit cell is the smallest repeating block. So when we will translate in every direction xyz, it will reconstruct the whole crystal without any gaps and overlaps. So we will see that in case of 2D and 3D, how many types of the primitive cell. And then next is the primitive cell. So the primitive cell is defined as the unit cell of the smallest possible volume. So it contains exactly one lattice point, and its edge vectors are called the primitive translation vectors like A, B, C. So for the 2D case, so first of all I want to define the previous lattice. So what is previous lattice? It is defined in, it is an infinity array of discrete points generated by, so like I explained that in any direction we can do the repetition. So by a set of fundamental translational operations. So on the basis of Brevis lattice, we can predict the electronic symmetry. Then and other macroscopic physical properties. So Here we have defined the five 2D Brevis lattice for the one square. So in square case, A will be equals to B, and the angle between this is phi is 90 degree. For the rectangular one, phi is 90, but A, the obviously for rectangle A is not equals to B. And the next is centered rectangular, in which there is one extra in the at the center there is one lattice point. Then hexagonal and oblique angle. So there are five types of 2D Brevis lattices, and so for example, graphene's honeycomb, it is form of a hexagonal lattice with a two atom basis. Next is 3D. For the three dimensions, we have the seven crystal system, and where we can find out the 14 Brevis lattices. So one is simple cubic, body centered, face centered. So simple cubic, and in body centered you will have one atom at the center. In face centered, at each face, so for the cube we have six faces. For at the center of each face you will have one atom like this. So like this we have, so we have uh, seven crystal system, that is triclinic, monoclinic, depending upon the A, B, and C. Then A is equals to B not equals to C. Like this, the cases will happen, and we can distinguish between the triclinic and also angles. So, since it is 3D, the angles is defined by alpha, beta, and gamma. So, depending upon how the angle is, we can define the lattice crystal system. Is it lattice, triclinic, monoclinic, orthorhombic, tetragonal, like this. Next is why size matters. So in the last class also we have proved that surface to volume ratio, we found out that as the size will decrease, the surface to volume ratio will increase. So if the surface area, so smaller particle size will give us the large surface to volume ratio. So shrink using this formula. So G is here, G is gives free energy. So if the radius will increase, then the surface term will dominate, and which will make the particle, which will make the entire different crystal phase to the stable one. Then effect of A on the nano size. So you can see that, so what is happening when we are moving from bulk to nano, the surface atoms, the surface atoms are since we saw that why the reactivity is higher in case of nanoparticles, that's why it is helpful for the catalysis reaction. So because when the surface atoms are have fewer neighbors than atoms inside the bulk, that's why the coordination number is less, binding energy is less. So that's why it, what will happen, the electrons will start moving inside the bulk, and it will start due to the surface stress, it will the particles will start bonding inside the bulk, and hence the lattice size will decrease. So that's why gold nanoparticles show the measured lattice contraction of zero point 0.5 to 1.5% compared to the bulk gold. So hence the smaller the particle, the larger the contraction. And you can see from this plot that the size is increase decreasing, the lattice constant is decreasing. Similarly, melting point depression, again at the surface atom the coordination number is lesser, the lattice binding energy is lesser, hence the low energy is required to break the atoms, meaning low thermal energy will be required to break the atoms, and hence the melting point decreases as the nanoparticle size is decreasing. So you can see as the weaker surface bonding pulls the lattice out of equilibrium, smaller nanoparticles melt at lower temperature than the bulk material. So you can see by this plot and this formula. So that's why we can control the phase selective synthesis by controlling the particle size. It is helpful for the catalysis reactions, and that's why we are using it is since the catalysis reaction is increasing nanostructured, we are using this in battery electrodes. And also in the last class we saw the super paramagnetism, from which was like in that we are not having forming the hysteresis loop in case of super paramagnetism. It had the shape of sigmoidal. So we saw that what major changes in the electrical properties, mechanical properties, thermal properties, optical properties are happening at the nanoscale. That's why dimensionality matters, because from the bulk to nanoparticles, quantum confinement is happening. That's why electrons are confined into one or more directions. Surface to volume ratio is increasing. Because of that, uh, there are changes in the surface stress, melting point, phase properties, and also this interface and the boundaries are changing. So scattering is increasing. That's why resistance is changing. Through resistance, if resistance is changing, then it will affect the electronic properties. So we have seen in the last class there's examples of 0D, 1D, 2D, and 3D quantum dots confined in all the three direction. Examples are cadmium selenide quantum dots, gold nanoclusters. Then one dimensional materials are nanowires and nanotubes, which is in which the confinement is in two direction, that is the in one direction the size is greater than 100 nanometer, and the example are carbon nanotubes, zinc oxide nanowires. Then 2D thin films and sheet where the confinement is only in one direction, and the example is graphene and MOS2. Then in case of 3D, where is nanostructure bulk, there is no confinement in any direction. Examples are nanograin metals and silicon. So we saw that through Drude's model, we were able to uh, define the Ohm's law electrical conductivity. So here we are explaining the resistance. So first of all, we are defining the conductivity, which is given by the n is squared tau by m, where n is the free electron density, e is the electronic charge, and tau is the relaxation time. So what is define the relaxation time? Suppose we have the inner tube, we have the electrons which are freely moving. So electron while moving inside that chamber, electrons are colliding. So if the electron is colliding with another electron or another atom, it is it is gaining energy and then again moving. So the time between the consecutive two collisions is defined as the relaxation time. M star is the effective mass. So, and in bulk, the collisions, since there are thermal vibration impurities also, and what we call the quasi particle of thermal vibrations are defined by the phonos. Thermal vibration, or we also say it as lattice vibrations. So now we want to see what will change when the conductor shrinks below 50 nanometer. So we have to define that this is the resistivity formula where rho naught is defined. So it will depend upon the free electron mean free path. So rho naught is bulk resistivity. So as the D will approaches this mean free electron mean free path, electrons electrons will collide much more often with the surfaces, so that the resistivity will rise above the bulk value. So here we have an example that if bulk copper has this rho naught with the mean free path of this, then if we have a 20 nanometer thick copper, it will give us this value. It means it is increasing the 3 times. But what is the reason of that? It is because we are confining the electron motion, and because of that, because of the electron confinement or quantum confinement, the surface scattering is increasing. If the surface scattering will increase, resistance will increase, and that's why the resistivity will increase. So when we are moving from bulk to nano, there is a drastic change, and from this example we can see that there's a change of 3 times. So we saw that the surface scattering will raise the resistivity below the mean free path. After that, it will there is no much change. This is I have explained. So these are the where we can all this where the properties of these nanomaterials we can use that flexible electronics, where we are using the graphene and nanotubes, energy storage in batteries and supercapacitor, solar cell perform for increasing the solar cell efficiency. We are using the materials, nanomaterials. Then optoelectronics and sensing. So we are using the size tunable quantum dots that will enable the that will help us to change the color. So it is using inquilat displays. Then also for making the highly sensitive sensors. Also, when we move to superconductors, there also if we are able to control precisely the quantum state, then we can use it as a superconducting qubits. So we are also using in the we can also use it as in the quantum computing. So next we will solve the problems. Let's take a 10-minute break. After that we will continue. Okay, let's start the assignment. So the this is the assignment number 2, in which the first question is, what is the key difference introduced in the Sommerfeld models as compared to the Druce model? So just now I explained. So first of all, what were the similarities? So both model assumed a constant potential And the Drude model didn't introduce, so it considered the classical statistics, that is Maxwell Boltzmann. And in the Sommerfeld model, it introduced the Fermi-Dirac statistics. So by introducing the Fermi-Dirac statistics, we assume the we consider the quantum statistics. So there is no role of surface roughness, there is no role of zero electrical resistance in case of Sommerfeld and Drude's model, and so the only difference was introduced in both the models was related to the introduction of Fermi level statistics, because in this model we considered electrons as fermions and we introduced the Pauli's exclusion principle. According to that, the occupancy cannot be more than 2. So both models assume that matter contains free electrons moving inside a positively charged ion background, and the major difference was how the electrons are treated. So Drude model it obeys the classical physics, and Sommerfeld model quantum mechanics. So what were the main assumptions for the Drude model? So positive ion is fixed, positive ion is fixed, and the electrons are moving free. So we are considering it as a free electron gas, and the electrons were moving frequently, colliding with the ions, and between collisions, electrons move freely. That this is what we explained as tau, that is the relaxation time, and so therefore it is classical. So Maxwell-Boltzmann statistics are used and considered the classical mechanics. So it this model could explain as the electrical conduction, that is without an electric. So if there is no electric field, the electron motion is random. If the motion is random, then the average velocity will be zero. That's why no current. But when we will apply the electric field, the electron motion will be in a particular direction, and it will acquire some drift velocity, which will be given by minus E tau by m, where E is the electric field, capital E is the electric field, small is the electronic charge, tau the relaxation time, and the then next the current density we can define as, so J is equals to sigma E. So after solving this, J is equals to n square tau by m. So we can define the electrical conductivity, which is very well explained by the Drude model. So this was the Ohm's law, which using this, if we are considering electrons as free under the constant potential, we are able to explain the Ohm's law. Then what were the shortcomings of the Drude model? So we are considering Maxwell Boltzmann statistics. So it means the there can be so many electrons and it is filled in the lowest energy state, but electrons are fermions, so they must obey the Fermi-Dirac statistics. And Drude, according to Drude model, electronic specific heat is given by 3 by 2 n kb. So which is not matching with the experimental results. That's why Sommerfeld model in 1928. So Drude model was given in 1900. After that, Sommerfeld model came and improvised some Drude models. That is, but he also considered the potential is constant and the electrons are freely moving. But he replaced the classical mechanics with the quantum mechanics by assuming that electrons are fermions, so that Pauli's exclusion principle is obeyed. Hence, why Fermi-Dirac statistics will be used and energy levels are quantized. So instead of Maxwell Boltzmann, now the distribution will be Fermi Dirac statistics. So now the electrons will be filled up to the EF, that is Fermi level. So at T is equals to 0, if T is temperature. EF is occupied and above EF it's empty. So according to Pauli's exclusion principle, no two electrons can occupy the same quantum state. With different spins, we can occupy it. It can be like this, but no two electrons like this cannot be possible. So and electrons will start filling from the, if suppose it is E1, E2, E3, hence the electrons will start filling from the lowest energy state like this. If there is same state, then this. So now the question arises, why only electrons near the Fermi level conduct? So because of the Pauli's exclusion principle, electrons cannot move into the occupied states. So electrons within the energy of kBt, the Fermi energy on the available energy states will be nearby that EF Fermi energy. So that's why, and it can only respond to the applied electric field. So this was the main thing regarding the Sommerfeld model. But also, since it is considered the constant potential, there were some problem that couldn't explain by the Sommerfeld model, which was the main problem was it couldn't explain the band structure. There was no concept of valence band, conduction band, and band gap. So it seems he ignored the crystal lattice potential that we consider the Bloch's theorem and KP model. So real crystals have a periodic potential due to the arrangement of atoms. So it was not considering that metal. So every metal was like a metal. But we know that we have semiconductors, insulators also. So it couldn't explain the band structures and why some materials are semiconductors, and couldn't explain the anisotropic properties. So the so for the first question, the answer is B. The quantum statistics and Fermi level was the main difference between the Sommerfeld and Root model. The next is, what is electron confinement? So electron confinement was when we were restricting the electron motion due to the particle size reduction. So that was the electron confinement. So we were not considering any magnetic field, not vacuum and heat. Only we are restricting the electron motion when we were decreasing the size from 1 nanometer to 100 nanometer. In this dimension, we were decreasing the particle size, and hence we were able to do electron confinement. Now, the third question is, the electron confinement occurs when the size of material is comparable to the electron's wavelength of light, mean free path, de Broglie wavelength, or energy gap. So the deep the correct answer is de Broglie wavelength. Why is this so? So quantum confinement will occur when the size of a nanoparticle will become comparable to the wavelength, since electron cannot no longer exist within arbitrary wavelength. So lambda is given by h by p, where h is Planck's constant and p is the momentum. So at the boundary condition, there is a formation of the standing waves that will result in the quantized momentum and discrete energy levels. So that's why de Broglie we can define the electron's wave function with the help of de Broglie wavelength only, and it will define when the quantum effects will dominate. Which quantum mechanical principle limits electron occupancy in energy states? Just now we discussed that that is Pauli's exclusion principle. So the correct answer is B. What does Bloch theorem describe? Bloch theorem describes the periodic wave function in crystals. So next is in periodic potential in electron forms what? Photons, band gaps, energy bands, or ionic bonds. So if so in a periodic potential, such as crystal lattice, electron will form the energy bands. Why is this so? Because of periodic arrangement of atoms that will cause the atomic energy levels to split and merge into continuous range of allowed energy. So suppose if an we are considering free electron, that is if we are considering isolated atom. So if we have an isolated atom, it will have the discrete energy levels E1, E2, E3. So electron, what will happen now? Electrons and it is given by E is equals to P square by 2n. Okay, so if we are considering the free atom, all the energies are allowed, and this there is no forbidden energy. But if we are considering the n square s square for one D case, if we are considering one atom, the electrons can occupy only these specific energy. Now consider two atoms together. When will two atoms approach each other, their electron wave function can overlap, and due to Pauli's exclusion principle, two electrons cannot have the same quantum state. So each atomic energy level will split into two closely spaced levels. Suppose two atoms E1, E2, E3. Okay. Now if we are considering, so when we are talking about the crystal, then many atoms form a crystal, and a crystal has 10 raised to power 23 atoms. Each atomic energy level will split into approximately 10 raised to power 23, and it will be very closely spaced levels. So these levels are so close together that they appear as a bands. And then what is the role of periodic potential? So when we are considering a crystal, the ions are arranged periodically so that the electron can experience a periodic potential according to the Bloch theorem. Vx is equal to Vx plus A, where A is the lattice constant, and that potential is repeating regularly. So now the electron will be defined by Bloch waves, and at a certain values of the wave vector. And what is that wave vector? That is Brillouin boundaries. So electron will undergo the Bragg reflection, and then the standing waves will form. So thus one energy level will split into two different energy, and that's why there is a formation of One is allowed band. Since the electrons will start occupying from the lower state, that's why it is occupied or partially filled, and then it is a conduction band, and the reason between these bands is forbidden, and this is the energy gap. So if we are considering the periodic potential, the electron will form the energy bands. Next question is, so we can also ask like why there are bands but instead of discrete levels, since number of atoms were 10 raised to power 23, so each atomic level will split into enormous number of nearly identical levels, so the spacing between will be very lesser and it will appear as continuous, and that's why energy bands are formed. The next is, what is primitive cell? So we saw that primitive is the smallest repeating volume in a crystal lattice, and we can understand is also like if we have a floor made up of identical tiles, so smallest tile pattern that is we are repeating to cover the whole floor, so that tile is our primitive cell. So it is the smallest possible unit cell. Also the properties are, it contains one lattice point, and we are repeating it by translation in all directions. That will recreate the entire crystal. And for example, we have the SC lattice, that is simple cubic lattice. So we can also explain like what is the difference between primitive cell versus conventional unit cell. So it is the smallest repeating unit, and this is chosen for symmetry. Also, it contains one lattice point, but in the unit cell, more than one lattice point. It can have a irregular shape, but unit cell will have like cube, hexagon, etc. So, why is it important? So, the primitive cell is used because it defines the periodic potential experienced by the electrons, and it is the basis for constructing the reciprocal lattice. Then which is helpful to define the brilliant zone and to study the electronic band structures. So the question was, what is primitive cell? So it was the smallest repeating volume in a lattice. The next question is, at a nanoscale, lattice constant tends to increase or decrease. So what is the effect of the surface stress on the lattice constant? So When we are talking about nanoscale, what is happening? At nanoscale, a large number of atoms are on surface, and surface atoms mm, have lower coordination number as compared to the bulk. Lower coordination number. What will happen if we have a lower coordination number? They can form the dangling bonds, because of that a surface tension will create, that is surface stress, that will pull atoms inward. So because of that, average interatomic distance decreases. If the average interatomic distance is decreasing, it means lattice constant decreases. Sometimes uh, sometimes this lattice constant, like there are some exceptions also actually. Sometimes lattice constant increases also if there are some defects or impurities, like if suppose if we have the silicon p type or n type, so then there are extra dopants, and if there is interaction with some substrate or thin films, and also there can be oxidation of the nanoparticle surface because of some, there are, because of these reasons sometimes the lattice constant increases. But the general property is, if the at nanoscale, if the surface stress, because of the surface stress the lattice constant will decrease. So like we saw in case of gold nanoparticles, it shows a slight decrease in lattice constant A as size decreases. So, what is the key takeaway? As particle size will decrease to nanometer scale, surface effects will become dominant, and this will cause a slight decrease in lattice contraction due to the surface stress. The next question is, quantum size effects dominate when size approaches nuclear radius, de Broglie wavelength, Avogadro length, and band gap width. So, we know the answer. Quantum size will dominate when the size will approach the de Broglie wavelength, because now the electron is no longer be treated as a freely moving particle; it is behaving as a confined wave. How can we explain? Like how can we think about that? So according to de Broglie, lambda is equals to h by p. So now every moving electron has associated wavelength. So when we are talking about the bulk material, for bulk material, that is L is very greater than lambda. Now what is happening? Electrons have Electron has a plenty of space to travel. It is behaving almost like a free particle, and energy levels are so closely spaced that they form a continuous energy bands. Now, when the size becomes small, nanoscale, L is comparable to the lambda. So, electron wave cannot fit arbitrarily inside the material. It is no longer free particle, and it will form the standing wave that satisfy the boundary condition. So only the certain wavelengths are allowed. L is equals to n lambda by 2. So energy will become quantized. E is equals to p square by 2m. So P is equals to h cross k. So now instead of continuous energy bands, we will get the discrete energy levels. So this is called the quantum size effect. So when this effect is dominating, when the size is approaching the de Broglie wavelength, and it will affect the optical and electrical properties significantly. So in case of quantum dots, we have the discrete energy levels. So it absorbs and emits only specific wavelength. That's why different size quantum dots emit different colors. But in case of a bulk semiconductor, it absorbs many wavelengths. That's why its energy bands are nearly since its energy bands are nearly continuous. So we saw that like if the quantum size if the size is approaching the de Broglie wavelength, quantum size effects are dominating, and that because of that confinement, that will change the material's electronic and optical properties. Next is which phenomena allows phase transition separation at nanoscale. So we saw that obviously all these things because of the nano size. Nano size means nanoscale. It means confinement, and confinement is reduced atomic mobility. So what is atomic mobility? It is the ability of atoms to move within a material. So if we are saying that this this has high atomic mobility, what does this mean? Atoms can rearrange easily. Low mobility means atoms remains nearly fixed in their position. So when we are talking about the phase transition, so phase transition, what does this mean? Involve a change in crystal structure. What does this mean? So for example, we have graphite to diamond, FCC to BCC, like face centered cubic and body centered cubic. So if some crystal structure is changing from FCC to BCC, obviously it involves a change in crystal structure, and if there is a reduced in atomic mobility, then there will be a separation of phase transition. So during these transition, if we want these transition to happen, atoms must move from their original lattice position to new ones. If atoms cannot move, a new phase cannot form. But at nanoscale, nanoparticles have very small dimension, few atoms, limited diffusion paths, strong surface effects. So that's why nuclei of the new phase cannot grow, atomic rearrangement becomes difficult, and the existing phase remains stable when even when it would normally transform. So this is called the phase transition separation. Next is as 1 by r square. increases, the lattice parameters tends to decrease. This is the same question again. Next is which equation relates melting point to size. See, we saw that Tm equals to Tm bulk 1 minus 1 by R. So if that will, so we can see that Tm is proportional to 1 by R. Next is why does resistivity increase in nanowires? So the resistivity of nanowires increases because of the surface scattering effects. So because electrons are, so what is happening in, if we talk about the bulk materials, in bulk materials electrons are mainly scattered by, first is lattice vibrations, that is phonons. Second is impurities like dopants, and third is crystal defects. So material is large, collision with the surface are rare. In nanowires, when the wire diameter comparable to the becomes comparable to the electron mean free path. So what will happen? Electrons frequently hit the wire boundaries. So that will introduce the additional surface scattering. So also, so if the more scattering means more electrons are bounded, it means they are not able to move freely, so resistivity will increase. Also, mm, grain boundary scattering. So many nanowires are polycrystalline also. So they contains many small grains and the electron will scatter at the grain boundaries. So more grain boundaries, more scattering, higher resistivity. So also because of surface defects, since nanowires have a very large surface to volume ratio, their surfaces can contain oxide layers, defects, surface roughness. So that will create additional scattering centers for the electron. So that's why the the resistivity will increase in case of nanowires. So what is the cause? Surface scattering. What is the effect? Increases electron collisions. Then if there are grain boundary scattering, it will reduce the electron mobility. If there is quantum confinement, that will affect the electron transport. If there are oxidation or surface defects, that will add more scattering centers. All are, because all of these properties, the resistivity was increasing. Next is one dimensional conductors. So quantized energy levels because of quantum confinement. This is the same question. And the forbidden energy regions between bands are called band gap. So we saw that atom was splitting into valence band, conduction band. These are the allowed energy state, but this is the forbidden energy gap, which is called the band gap. So now with this, the assignment is completed. What are the key takeaways from this? So we confine an electron. So we talk about Root model, Sommerfeld model. Because of then we considered the quantum mechanics, and using the periodic potential KP model, we saw that if we are confining an electron, it is the energy is quantized. It means if we are shrinking the dimension towards the electron's de Broglie wavelength, it will turn from continuous free electron behavior to discrete atom-like levels, where the energy was given by n proportional to n square by a square. Second is periodicity will, if we are considering the periodic potential, that will create the bands and gaps according to the Bloch theorem and KP model, which that shows that why a periodic lattice produces allowed energy bands separated by the forbidden gaps, which is the origin of metals, semiconductors, and insulators. Next, we define the crystal, that is defined by the lattice and combination of lattice and basis, the how many symmetries are in the 2D and 3D, and how the size will dictate the crystal structure. Then what are the effects on the lattice dimensions because of the surface scattering, surface stress, phase transition, and the melting points at the nanoscales. Then how the dimensionality is reshaping the electrical behavior. So we saw that the resistivity changing if we are moving from bulk to at nanoscale. So we saw that the thermal, electrical, optical, and mechanical properties are changing very significantly from their bulk counterparts. So in the this is what about the today's lecture. So we will meet the next week again, in which we will discuss about more of the what is the what are the even how can we define in 2D and 3D model, also nanoscale properties, how these are changing. So this is all about the today's lecture. Thank you. If there is no question, then I am leaving. Okay.